Sounds great. Thank you so much. And just to do a voice check, can you hear me all right?
Yep, we can hear you.
Perfect. All right. Well, good morning or afternoon, wherever you are in the world. I'm Tim Chung. I am a program manager at the Defense Advanced Research Projects Agency, or DARPA, and it's definitely a privilege to be speaking with this group, in particular about subterranean robots that have to go off into the unknown underground. And the context in which I'll describe this effort is in the context of the DARPA Subterranean Challenge, which many of you may be familiar with. And so I'll describe a little bit about the challenge itself, but really the motivations behind it and all the lessons learned. In fact, I won't say all the lessons learned. We're still learning many lessons, but just highlight a couple of them. So in particular, what we're interested in for the Subterranean Challenge is to inspire and discover those types of robotic technologies without necessarily prescribing what that solution is going to be, that will enable us to provide actionable situational awareness. And I'll describe what I mean by that, across diverse underground environments. And so the key takeaway I think here is that it's not just about getting robots to work in a single known environment. And I think that's what field robotics is all about, is there's just so much uncertainty out there. How can you design your systems to be resilient to that uncertainty? And so one of the areas of uncertainty is that when one goes underground, there's just so many different ways to think about underground. That could be human-made tunnel systems, think of mines, urban underground, everything from transit to infrastructure, sewers and drainage and things of that nature. And then of course, nature has its own version of what it defines as underground, being naturally occurring cave networks. And so what's fascinating, I think, about this is that these are all underground environments. They all have very similar challenges, but they also have incredibly unique signatures that thwart, I think, many of our best efforts to develop technology that's going to handle all of these subdomains, all of these environments. So to frame how we wanted to define the problem we want to solve, here's an example scenario. And of course, there's scientific value to going underground, for sure. One of the other arenas, of course, is in that scenario where you have a first response or security mission that's of interest, and we need to deliver what we call actionable situational awareness for these very challenging, unknown, and dynamic environments. And in particular, it's pretty challenging to send humans in there at first blush to be able to do that. And so kind of looking at the spectrum of scenarios where one might send robots in underground settings. On the left, you have these really long lead time, very deliberate, you can plan in advance. You probably have known maps and things of that nature, but this is where you're trying to conduct inspections, or maybe those scientific missions where you don't have maps, but you can take your time. On the extreme right-hand side, you might see the case where you have an intervention that's absolutely immediate, that's necessary, and you're just going to accept that risk and send people in there because you know that there's somebody else's life might be in the balance there. So we're interested in the more prevalent scenarios where you have anywhere from, let's say, just shy of an hour to a couple of hours in response to some disaster emergency scenario. That incident commander is standing up an emergency operations center, and in that 1 to 4 hours or so, that golden hour, if you will, as she's marshaling her forces and figuring out who needs to go where, wouldn't it be great if we could send in robots to be able to get a lay of the land in an hour before we know enough to send in people, and have that information be made available to expedite and make safer the mission at hand. And so that's really this window that we're interested in. Time pressure is there, uncertainty is high, there's still risk. We just need to assess where and what kind of risk there is to the first responders that are going into these sites. All right, so now that I've given the time pressure associated with it, here's what I was alluding to earlier. There are a number of common characteristics, unifying characteristics, that all of these underground environments will certainly present. things like confined spaces, things like really challenging visibility. And I'd say that unpredictable communications is probably one of the more gnarly ones. Things like the geometry of these environments, these are also problematic. But that's just one element. Now you have things that where these environments are incredibly different. And part of it's just the degree of differences that one might be able to find. And I really think that challenges of scale, anything in the field, I think you really want to think about the impact of scale, both spatial and time, to really understand what happens. The fact that you might have incredible verticality versus twists and turns. And so just to highlight that diversity, you can kind of just look at the different ways in which caves, tunnels, and urban environments tend to get structured. And just based on that alone, you can imagine the design of your systems, your robotic systems needing to be particularly tailored, but somehow you still want them to be all around best athletes to be able to conquer what they might not yet know they're going to find around the corner. And so to tease out, looking at what we just saw on those charts, teasing out what are the things that really mess with robots, as we all know. And so everything from lighting conditions, so dynamic lights really stress our visual sensors, particulates in the air, whether that's smoke or fog, or even it's the dust that we kick up ourselves as we're moving through these environments. Obviously water, mud, other kinds of environmentals that could be problematic. And then the geometry and the terrain. There's just such a wide diversity of things that one could face when you're dealing with 3 dimensions going underground. And so just to highlight here, everything from stairs to shafts to stopes and ledges and things of that nature. Really hard to wrap one's head around how to cover all your bases when you're going through here. And so the nature of a DARPA challenge, of course, is to drive technology innovations. So you take a look at these challenge elements and you tease out what are the key technology areas that really need a major push forward, a step level change to be able to have a dramatic impact. And you kind of figure out, well, clearly the terrain and the way that environment changes as you move through it, the fact that there's no GPS under there in underground settings, and oftentimes it's really hard to get a fix. It's very easy to get turned around. Sensing, comms, the fact that you might be underground for hours at a time, that's particularly challenging, of course. And then the terrain itself, you just never know what's going to happen. And so the key takeaway on this chart is, how do you tease out what are the technologies where if you had 1 unit of improvement in this technology, you can have an outsized high gain response to the types of capabilities you can bring to the table. And what the DARPA Sub-T Challenge highlights is that you can't just do it in one technology area. In fact, you need to be able to advance autonomy, perception, networking, and mobility, all 4 of these technology areas. And you can't even do it in piecemeal manner. You really want to think about how can you do this in an integrated, coherent, holistic way to really elevate the level of capabilities that you bring to your robot or fleet of robots. And so now that we have these technology areas, now we get to go and ask what are the big open questions. I'm only listing a handful here, but clearly there are enough to feed dozens, if not potentially hundreds of dissertation topics and papers, among other things. But just some of these questions, and I'll just highlight, how do you optimize between exploring versus exploiting the information that you might have? We tend to think a lot about gathering information, sampling, information gain. But there's also this question of what's the most meaningful information that you want to get and for what purpose? And that's really where this exploitation of that information is key. I think that's especially relevant in underground environments as well as other field applications, because again, you have limited time and limited resources, limited number of field trips you can make. So you really want to optimize not just the amount of data you collect, but the value of the data that you're collecting. And then the other one I'll hit upon here is heterogeneity. Heterogeneity means diversity in platforms, diversity in sensors, diversity in algorithms and approaches. There's just, how many tools can you fit into your tool belt to be able to bring to bear when you're out there in the field? And so thinking through these tech areas and associated relevant measures, clearly there's overlap between how autonomy impacts perception, or how perception is impacted by the ability to transmit information to networking. And of course, you need to be able to get there with your mobility solution. So thinking through these metrics or measures is absolutely key in designing your systems, knowing what it is that what problem you're trying to solve. Okay, so that's at the very high level of, here are the characteristics and kind of questions about underground environments. And so how did the Sub-T challenge formulate and construct this problem? Well, the DARPA's Sub-T problem was this notion of providing actionable situation awareness in these underground settings. And we define actionable by saying, hey, you're basically going to go conduct this underground scavenger hunt in a fixed amount of time. You have to go find these things that DARPA's called artifacts. You have to do so by identifying them correctly and also being able to position them accurately to within a 5-meter error bubble. All right, so now we're going to go conduct these underground scavenger hunts type of idea. I give you an hour, go find as many of these objects as you can. And so one of the other things to note here, though, is it's not just one type of object that you have to go find, but in fact, on this left-hand side, you have a variety of artifacts that you might have to go find, and they have very different characteristics. So of course, we might want to go find something that emulates a survivor. So that's a human-looking figurine, that a mannequin that clearly is indicative of somebody needing rescue. And you might be able to use a person detector from your best camera visual detector classifier to be able to do that. But this thermal mannequin presents a thermal signature. It also has a voice box so it can sound alerts. And so now you can imagine thinking about other cueing and other sensors to go and try to do that classification. Similarly, things like the cell phone. Yeah, that's going to be really hard to pick up on your camera, but the fact that the Wi-Fi is in hotspot mode and Bluetooth is in discoverable mode means that maybe you can use an RF sensor to be able to geolocate this particular artifact as well. And another example here might be a gas artifact. So DARPA instrumented the various courses to be able to emit, in our case, say CO2, but you can imagine this being a surrogate for either noxious gases or dangerously low levels of oxygen. And so now your sensors on board your robots now need a CO2 sensor to be able to divine where these artifacts might be located. And clearly you don't want to leave any points on the table, points being if you report that back to DARPA where an artifact is correctly located, you don't want to leave that on the table by not having the appropriate types of sensors. So being able to understand what that means is critical to doing well in this type of a competition setting. And so this challenge is structured in a way where it is interested in, of course, being able to specialize in some extent. To some extent, we are interested in technologies that will benefit in these different subdomains. And so we constructed this in the context of a tunnel circuit, an urban circuit, and a cave circuit. Think of this as kind of the triathlon of underground scavenger hunts. But it isn't good enough to just dominate in one at the expense of the others, because the final events, which we conducted just a few weeks ago, it incorporates all three of these subdomains. And so your best bet is, rather than being just the best runner or best cyclist, it's much better to be the best triathlete and think about the design of your systems to be resilient across the uncertainty and the distinctions between these three environments. I'll say that the Sub-T challenge had both a systems competition where we're building and breaking real robots, and also a virtual competition where we could really push the limits based on our software-based solutions for autonomy and perception. And so I will say, of course, much like many of us with the global lockdown, we were not able to conduct an in-person cave circuit competition event, unlike the tunnel circuit where we conducted it in a coal mine, and an urban circuit where we conducted that in an unfinished nuclear power plant. Cave circuit, unfortunately, only had that virtual component. But I will say that many of our systems teams, recognizing the up-tempo, the drumbeat of field experimentation that's required for field robotics, took it upon themselves to go out there and find caves and local caving clubs to go and test out their systems in cave environments as well. And so, rather than describing that experience, myself, I want to share a quick video that highlights, I think, some of the experiences and the lessons learned of many of our teams, I'd say, of being able to work in underground environments.
Challenge is about developing and defining the problem, not about defining the solution.
This challenge has the opportunity to create that environment for innovation.
I think that the toughest thing academically about this is having multiple robots work together with very limited human interaction.
You can't just have one thing work, right? You have to have 5 different things simultaneously working. And getting to that point is extremely non-trivial, but I think that that's ultimately the real value.
We love this challenge because it allows us to emphasize on the hardest problems in robotics at the moment, in mobility and autonomy, and emphasize on how to solve them.
We think that the virtual is a chance to showcase ourselves.
Clearly, this is the world's top research group, industry group, coming together to solve this unique challenge.
So you heard from all of our competitors there, just really what the impact of trying to work in these challenging environments really is. And to that end, one of the things that we did from DARPA's perspective was needing to envision how to test for that resilience across all 3 subdomains. In particular, where in the world could one find a place where you could get tunnels, urban environments, and caves all next to one another? And if anyone out there knows, please let me know. I still have yet to find such a place. And so what does DARPA do? Well, we're interested in creating and we fabricated this one-of-a-kind sub-T environment, specifically taking over a limestone mine and fabricating this course that you can see on your screen here that kind of stitches all of this together in a way that really allows for our competitors and researchers to be able to stress test their systems in true fashion of trying to be resilient across these different subdomains. And so again, just to highlight what that looks like, I want to share with you what this fantastical one-of-a-kind course was with a short video here. So here we are, that's the staging area. We're about to cross into this threshold. No team, no robot is aware of what lies beyond that threshold, beyond what you can see from that staging area. What I'm showing you here are scenes of the site of the venue that we fabricated. You can see that survivor hidden around that pillar. Here's an example of a tunnel segment that's replicating a hard rock mine, for example, and trying to navigate in these kind of environments as well. Everything from rails to low lighting, to a lot of debris scattered all throughout. DARPA also went and I visited numerous cave sites, crawled around on my hands and knees and elsewhere on my tummy and trying to find what a representative cave might be, and brought all of that back to be able to fabricate this kind of a large cavernous course coupled with really highly confined spaces. And so I think we have a lot of videos online that you can go take a look and see exactly the full length and scope of that course. But I can assure you it was quite a lot of fun to both see and put that together, but also see robots try to make it through that course. Okay, so now having talked about the challenge and the nature of field robots there, wanted to just spend a few minutes talking about the kind of technologies and the lessons learned. So in particular, I think one of the main takeaways is thinking about how you can balance the capabilities that you might have from one or more robots that you bring. And so we did see a lot of this style of marsupial deployments, being able to leverage, for example, a drone on the back of a rover, on a UGV, and allowing for one to balance the strengths and weaknesses between these two different types of robots. So from that point of view here, you see a tank, a tracked robot deploying a vertical robot. You can just see by how this robot, this drone is flying all around, the expansiveness, the verticality, kind of looking into all the nooks and crannies. Of course, all of us watching this are rooting for it to go down this open shaft to a lower level. And of course, the drone won't disappoint as it descends. And in fact, out of communications range, is able to go off and explore in greater detail in underground environments. But having been able to get there with that ground robot in the first place, I think was pretty critical. Another interesting technology advancement, I'd say, is the overcoming of mobility hazards with the advancement of legged robots just in the 2-3 years that this challenge has been going on. So on the left, I'm showing you the tunnel circuit, where we did see some legged robots make an appearance early on and really get stuck, quite literally, but also figuratively, in what they're able to deliver. And that tunnel circuit was back in August of 2019. On the right, I'm showing you footage from our recently concluded final event, where a vast majority of our teams now fielded legged robots. And here you see a four-legged robot that is able to, out of communications range, by the way, this is deep enough in the course where a human's not even able to recognize that this has happened, but the ability for this legged robot to understand that it's tipped over, rectify and recover, and even now realize that it still had more to explore, will go off and self-figure out that it's going to go climb this 45-degree incline to go solve the problem of mapping extensively. So seeing that evolution has been pretty remarkable on that level of maturity. And this is just another platform demonstrating its agility going up that 45-degree incline that we created for it in a pretty tight space. And then another technology area I think that's representative of being out in the field, of course, is what kind of quality of information you can provide. And so here are some of the mapping results from the systems teams as they're going in there. And so just imagine what it takes for a human to go crawl through these environments. I can say it took about 100 hours for our human team to go and scan this, whereas we see robots now collectively being able to do this in under an hour. So I think that just highlights the potential role that robotics in these austere environments play, but also how far they've come in being able to deliver capabilities that are of import to end users. So I get to highlight now the key takeaways. I'd say, just kind of thinking through all the lessons we've learned, I think one of the things that we've both telegraphed, advertised, and witnessed all throughout the DARPA Sub-T Challenge has been that attrition of robots is not only possible, but likely. So how do you think about your team in the face of the likelihood of attrition? That includes everything from not putting all your eggs in one basket, meaning likely not putting all of your sensors or all of your exquisite capabilities on one platform, but instead distributing or dispersing that capability across multiple platforms potentially. How do you develop redundancy? How do you deal with that possibility of loss? Another lesson here for us is multimodality. The ability to kind of diversify how you think about solving the problem is absolutely critical. Not only at the big picture level of autonomy, networking, perception, and mobility, but at the sensor level, where you might have different sensors on board different robots. You have different communication approaches, multiple radios, different frequencies, even in fact, different strategies for what information gets communicated over what channels. Clearly, being able to leverage heterogeneous locomotion modalities is key to be able to handle those vertical shafts alongside the long transit distances that you might need to deal with. And then resiliency in terms of robustness and decision making. So you might want to rely on full levels of autonomy, like the previous speaker mentioned. There might be opportunities where you want to take advantage of that, but there might be other times where you want to involve a human supervisor, and it might be splitting the load, not on exploration, but maybe on classification tasks or something along those lines. So being able to balance that and dial that knob on the fly is absolutely critical as well, so you can adjust to the mission at hand. And then finally, I'd say it's not just about what robots you bring to the mission, but how you use them. And so, I mean, here, there's strategy and gameplay here that you want to think about for being able to deploy your robots. Do you want to send out the fast-moving scouts first, even if they lose comms and might not come back? And you lose all that information that they might have collected, or do you want to send your slow-moving, concrete, hard robots, hardened robots? But if they go down early on, they're going to block the way for all of your following robots as well. So there's a lot of interesting strategy to think about. And that's really, I think, where we want to move towards for thinking about field robotics. And so I'll close by just highlighting that the nature of field robotics is that, data is not easy to come by. That's why we're out there in the first place. And so one of the things that I've been pretty passionate about, as has the Sub-T community, is developing and curating data sets of these types of environments that it's really hard to get to. So we've published and released everything from our professional grade survey data to point clouds to other types of visual data sets, including reference robotics data sets for example, SLAM benchmarking. And then from our most recent final event that was recently conducted, an immense volume of data collected by ourselves, as well as the teams who I know are eager to publish those data sets for communal benefit as well. And so with that, highlighting that community, here's a look at, I'd say this cadre of Sub-T roboticists ready to go out into the field and understand both the good and the bads of being out there in the field to do this kind of work. And with that, I'm excited and eager to take any questions that the audience might have. Thanks for the opportunity.
Thanks, Tim. That was great. And we had an absolute ball participating in the challenge. Does anyone on the meeting have any questions for Tim? You can ask them on the Zoom chat or on Slack. All right, so there's a question, I'll read it out from Maurice. What next for Sub-T explorations? Do you know of efforts to keep this community together? Could other countries host follow-on activities?
Yeah, I think I missed that question. Can you say that one more time for me?
Yes, so the question is, what next for Sub-T explorations? Do you know of efforts to keep this community together? Could other countries host follow-on activities?
Yeah, no, thanks for the question. So absolutely, I think, the community is excited and thirsty and hungry for more. I keep hearing that if we only had one more year, how much more could we do? And I absolutely agree with that. I think the community is ready to be able to go off and conduct those kind of events or field campaigns or competitions. So to that end, I'd say a couple of things. One is the virtual side of the competition, the Sub-T virtual testbed, which I didn't talk about in the context of field robotics, of course, but that one is completely open source based on Ignition and ROS, available. All of the worlds that I described where physical robots had to go off and conduct these tests and missions are also available in high resolution in the simulation as well. So at a minimum, you should be able to pick up the Hello World example and develop robotic algorithms to work in the environments that these physical systems have deployed as well. And I really do think that if you look around every corner, there's a cave, a tunnel, or a parking garage, underground parking garage near you. And being able to find and understand the challenges of underground robotics, I think is a lot closer than we might think of otherwise.
Yep, thanks, Tim. And just for the benefit of everyone who's on the call, a number of teams that participated in the finals along with Tim and DARPA, we are in discussion to have some sort of a summit with the participants where we could more broadly discuss lessons learned and then field questions from others as well. So just watch this space. We'll announce things as they come. And while I thank Tim again, I'll introduce our next speaker.